nice to be here in this beautiful observatory. So Ramon said most of my affiliation. I started like working on volcanoes because I was interested in volcanoes when I was young, and I ended up working on the gas from the solar system. So it's my evolution. All right, so I will talk about. Okay, so what I'm going to say, we recently published a review paper in Nature last month, actually, and part of the information I'm going to tell you is partly in this paper. So if you're interested, I can, of course, send you a reprint, no problem. Okay, now it works. So life-forming elements are, as you know, hydrogen, carbon, nitrogen, oxygen, sulfur, and so on. And in fact, what is remarkable is that these elements form the composition of the atmosphere and the ocean, H2O, CO2, and the noble gases. But in fact, these elements, and of course, these are the cradle of life that permitted life to exist on Earth. And but in fact, if you look at the composition, as you know, the composition of the gas that is present in the universe is mostly hydrogen and helium. That makes 99% of all this gas. So this giant cloud of gas that are made essentially of hydrogen and helium with a little bit of dust, maybe less than 1% dust. In fact, they do not resemble at all about the volatile that permitted the development of life on Earth. So in some way, my talk will be about trying to suggest some ways to starting from the protosolar nebula to obtain this gas that can be used for the development of life. So one can start with the abundance of the elements in different cosmochemical reservoirs. So these are the abundance that are normalized to silicon, one of the elements. And it's normalized to silicon and normalized to the composition of the protosolar nebula. So the nebular gas from which the sun forms and which is inherited from the universe. Okay, so here means normalization, means solar nebula is one by definition here. And here are plotted the different objects and reservoirs that we can find in the solar system. Primitive meteorites, I shall come back on this. And also the composition of the Earth, the bulk composition of the Earth for some of these volatile elements, helium, carbon, nitrogen, oxygen, and noble gas. And it's immediately obvious that the composition of the Earth and solid in the inner solar system is exemplified by primitive meteorites are very different from the composition of the gas, of the initial gas. They are highly depleted and they are highly fractionated with respect to each other. So there must have existed some process that resulted in this fractionation. And this is about my talk. It's first, I will show, as you probably know already, that the so-called planetary volatiles that we find in inner solar system bodies is completely different from the protosolar nebula, from the abundance, but also from the isotope composition. And I will also talk a little bit about the origin and the process that resulted in this composition. So just to start from the beginning, you better know than me about this process here, but so it's the view of a geochemist, so it's quite naive. But the system started when a cloud of gas and dust started to accumulate, giving rise to a dense molecular clouds, and local contraction give rise to stars and a disk of gas and dust. Okay, Now, thanks to the James Webb Telescope, we have nice views of this formation. And so to make it simple, quite schematic, so a molecular cloud core started to collapse, forming a central star, first heated by gravitation, and later on a disk of dust, and mostly gas and dust, on which the cloud continued to fall lower down. And in this system, you had always, or probably, you had ionization, irradiation by nearby star, probably, or by the central star that took place. And this irradiation probably resulted in photochemistry that I think is the key of the fractionation of these elements, or of the volatile elements. All right, so to make things quite simple, so you have the central star, you have a disk that forms, processing, turbulence takes place, mixing up everything. Some parts are preserved, and still you have some ionization sources from the star itself or from nearby stars. And then there is also a gradient of temperature that takes place with dust setting taking place here. We have what is called a snow line, that is an area where beyond which ice, water ice, and CO2 ice and CO ice can exist. And closer to the star, the gradient of temperature prohibits the existence of such of icy grain. It probably also had a tar line that is a limit within which organic matter could exist and was completely dissociated closer to the star. And it's, according to some models, it's likely that this kind of condensation fronts favored the formation of planets, with the giant planets already existing quite early in, and far from the system, some icy bodies that are now represented by comets developed. And if we have a look to the system, another very important testimony of this epoch were the meteorites, especially the chondrites, which are primitive meteorites. They kept the composition of the material that existed about 4.56 billion years ago, up to now. So these are really very interesting traces of the composition of the matter at the time. And they do contain some volatile elements. Oops, sorry. They do contain, some volatile elements which are mostly concentrated in a kind of low temperature matrix. It's an assemblage of shaly water altered minerals that are full of OH or full of organics and so on. And the composition of this meteorite will give us a good indication of what was a primitive material once the solid formed. Some of these meteorites, so-called carbonaceous chondrite of type CI, are volatile rich. They can contain up to 15% equivalent H2O and 5% carbon as organics. And obviously, they are good candidates to have supplied volatile elements to the Earth and to terrestrial elements. All right, so as you know, of course, this meteorite or the parent bodies of this meteorite are now concentrated in a so-called asteroid belt, which is located between Mars and Jupiter. And sometimes these planetesimal are disturbed by interaction, gravitational interaction, and come close to the Earth and could become a threat to planets. Okay, so knowing precisely the composition of this primitive material has attracted a lot of attention. So you can get this material just by looking at meteorites that fall down on the Earth But doing so, they are degraded by interaction with the terrestrial environment, especially the volatile-rich meteorites that are quite fragile. And so there has been several efforts trying to pick up some material directly from planetesimal, from small planets. And one of these is the Hayabusa mission from JAXA, which was the first sample returned from a mission from a volatile-rich asteroid. It's from the Japanese agency, JAXA. And it landed on Earth 2 years ago in Woomera Desert in Australia. 5 grams of sample were recovered, which are here. It's kind of black material that is rich in organics and silicate, magnesium-rich silicate. And since then, these samples are distributed worldwide. And this material sampled in asteroid Pyogu resemble to the CI type material, the one which are rich in water, carbon, and nitrogen. So our lab has been involved in such an effort. In fact, we analyzed some of the grain. So this is a team, and you see that there is a dress code with having sweater with stripes, which is quite mandatory. And since then, there is another sample return mission that is quite important too. It's called OSIRIS-REx, and this time it's a mission from NASA. It's about a similar type of mission. Also going to, it has already sampled a volatile-rich asteroid called Bennu, and it's coming back to Earth, and it will land in September next year. So that will be another fascinating mission coming. At that time, it has sampled more than 200 grams. So in one case, we have 5 grams, and here 200 grams.
Do you remember where the landing site is?
Yeah, it's Utah Desert. It's
Utah
in a base, in a US Army base. But even when you have 5 grams, it's already a lot of material, because here, for instance, we work with less than a milligram sample, and we have enough, plenty of volatile elements in such a small sample. Okay, so these are the meteorites, first indication, but you have also further out icy bodies that are now sampled by comets. And the comets are made of, we can say, 20 or 30%, up to 50% ice, mostly water ice. And they are also good candidates for providing water to Earth. And here again, there has been a very nice sample return mission, not sample return, sorry, exploration mission from the European Space Agency that you have heard, with a NASA participation, then went to explore Comet 67P, Churyumov-Gerasimenko. It was launched in 2004, it traveled for 10 years, and then it has been flying over the comet during several months in 2014. And there were a lot of instruments on it, and there were mass spectrometers to analyze the volatile element. And I will tell you a few results of this exploration. Unfortunately, we don't have yet a sample mission to analyze cometary sample in the lab. Okay, and those samples, of course, are from different parts of the solar system, and the people doing modeling dynamics of the early solar system, like Ramon, Steve, and people in France, like Morbidelli, they argue that the giant planets were not very stable at the beginning. They've been moving, and doing so, they perturbated the cometary disk, sending a cometary body to the Oort cloud or the Kuiper belt, but also perturbating the asteroid belt and sending or favoring the sending planetesimal and asteroid towards the terrestrial planet zone, which helped, in fact, to build planets. All right, now I will go to our favorite tracers, because we are working with isotopes in our lab. It's a kind of specialty. And so just to remind you, the isotopes, these are the isotope of hydrogen. Hydrogen this is the simplest element. one proton, one electron, and deuterium as in addition as a neutron, which has no chemistry. So the two isotopes are the same chemistry, but the ratio between deuterium with a neutron and hydrogen, I will show you that it shows a huge variation in the solar system. So these are traces of origin and also processing, because this isotope ratio can also vary according to physical process. All right, so to start with, these are the DOH ratio in the solar system. Okay, represented here. This is a paper by Catherine Albeck. It was a paper with the data from the comet 67P here, and there are several remarkable features. The protosolar nebula, which is best characterized by the atmosphere of the giant planet, which are made of the nebular gas here, and also from the analysis of the sun itself and the isotope ratio of deuterium of helium and hydrogen. Anyway, so the protosolar nebula was here and poor in nitrogen, in deuterium. And in fact, this is a composition of the terrestrial ocean, which is a kind of reference, and which is about 6 times more rich in deuterium as compared to the starting gas. So there's been some process or some heterogeneity that enrich a lot the inner solar system represented by Earth, and also represented by primitive meteorites that was able to enrich inner solar system bodies in deuterium by a huge amount. And finally, you have another very interesting reservoir, which is here. It's a cometary reservoirs. So most of comets are rich in deuterium, are even richer than the Earth and just looking at the, sorry, at the time. So, okay. So there is a huge variation of the DOH ratio, which seems to be heliocentric, that is increasing with the distance from the sun. And in fact, for nitrogen, there is a kind of also isotopic variation of nitrogen in the solar system that mimic in some way those of hydrogen. And in fact, from the analysis of inner sample, we know there were a huge variation of the nitrogen isotope composition. There are 2 isotopes, 15 and 14. But the cause of this variation was not really known. And it becomes clear, in fact, thanks to another space mission that we call Genesis. That was a mission from NASA, which sent a spacecraft in a Lagrange point L1, I think. It stayed here for 3 years, collecting ions emitted by the sun and the solar wind. And this was a beautiful experiment to know better the composition of the sun in terms of trace elements and in terms of isotope ratio, particularly oxygen and nitrogen. So these were the panels that were exposed to the solar wind here, ultra pure material. And for the story, the spacecraft was a sample return capsule. After sampling, this was folded and came back to Earth. And the capsule was supposed to be aimed by a helicopter to prevent too much contamination with the terrestrial environment. In fact, it completely failed because the parachute did not open. And so the capsule crashed in the Utah desert. And so it was a kind of catastrophe because this material, supposedly very pure and clean, was completely broken. But nevertheless, the analysis could be done because the solar wind was implanted at depths of several tens of nanometers, whereas the pollution, the absorption just concerned a few nanometers. So it took a very long time for the teams involved to analyze the composition of the solar wind ions implanted in the target. We were part of this experiment in Nancy. We used an ion probe to dig into the sample. This is a, oops, sorry. yeah, we use an ion probe to the sun. This is one of the samples broken, but we could nevertheless get the data. Okay, so now this is the same diagram or similar diagram as the D over H. In that case, the logic of the diagram is that going up, it's nitrogen 15 rich. And so the genesis data allowed to define what was the composition of the protosolar nebula, because the sun makes 99% of the material now in the solar system, and it's the best representative. Oops, what's happening? All right, so okay, so the starting composition of the solar system of the nebular gas was here, and then the inner planets and asteroids represented by meteorites are mostly here and reached by 60% in nitrogen 15. And finally, the comets again are rich in nitrogen 15, and all the comets including 67P. All right, so we get about the same logics as for the D/H ratio, is a kind of heliocentric gradient. And obviously what we can do now, we can just combine the two systems. Oops, sorry. Combine the two systems. So the D/H ratio as X and the nitrogen 15 over 14 as Y. Okay. So again, we have the starting composition of the solar nebula. And Jupiter, by the way, has the same nitrogen isotope composition as the Sun, which is consistent with the fact that Jupiter has trapped some solar gas. Okay. The Jupiter atmosphere is from the nebula. All right. So afterwards, so this is the starting composition. Here we have the inner solar system as represented by the Earth and meteorite and the Moon, in fact, also. And finally, we have the outer solar system, which is represented here by comets. So just by looking at these stable isotopes, it's quite clear that the terrestrial volatile, at least for the H and therefore H2 and nitrogen in the atmosphere, have mostly affinities with inner solar system bodies, which are now represented by meteorites. So the bottom line would be that the volatile were acquired from the inner solar system, from some reservoirs that was already fractionated, modified from the protosolar. We can go a little bit further, and now we are going to use one of our favorite tools, which are the noble gas. And by the way, if you have a question or something that I'm okay, please ask me now. I don't mind. Yeah.
So if Jupiter and the Sun are the same,
the same composition, that's
same
hydrogen
15 to 14 against hydrogen isotopes, then why are the comets so different? Is that because of the physics of the ice and the absorption of gas on the ice, because there's a phase separation? Because you would presume that they formed in a similar region of space.
And this is because the comets are not made directly from condensation of the solar gas. And there is an intermediate step that fractionated the isotope while forming ice that I will go now describe. That's the main reason. I'm just checking for the time. Okay. All right, so we use a noble gas because these are wonderful elements which are physically inert. They have no chemistry. So they only record physical process like kinetic fractionation, nuclear reactions, that is, for instance, radioactivity, cosmic ray production, that produce some of the isotopes. And also, they are made, like every element in the solar system, from different stardust, from different stars. And so the isotope composition can be heterogeneous, depending if of the nucleosynthetic mix. And I will start by first by looking at limits of it, by looking at neon in the terrestrial mantle. So it's a little bit of a digression, but these are neon has 3 isotopes, and the bottom line is that if you represent, for instance, you normalize to one of the isotopes, here neon 22, and if you have a mixing between 2 poles, you obtain straight line. It's just by construction of such a diagram. And here are represented the atmospheric composition of neon, the atmospheric composition of the solar nebula, and these are sampled from within the interior of the Earth. These are either volcanic gas or gas that are trapped in volcanic rocks, mid-ocean ridge, mantle plume, and so on. And what we see is that we have a lot of variation that can be understood as mixing. As I told you, we have a mixing will result in 2 poles, will result in 2 straight lines. So here are represented some from mid-ocean ridge, convective mantle, also from the deep mantle. And in fact, what we see here is that we have excess of neon 21 with respect to neon 22 this way, but these excess are due to some nuclear secondary reaction in the mantle that produce neon 21. It's called nucleogenic production. So this is a geological process. But if you look, oops, okay, now this is a synthetic diagram, the same one. If you look at neon 20 to 22, there is no process that can produce neon 20. So this means that going up in this diagram means that you have to mix with something that is rich in neon 20 compared to Earth. And in fact, it is the solar nebula. So in this diagram, all the variation can be understood between mixing between atmospheric neon, because atmospheric gas are ubiquitous in the Earth, in the Earth's interior. There is hydrothermal circulation and so on, so there's always some contamination. But what is important here, you have a pole rich in neon 20, which is identical to the solar. And this means that, in fact, within the Earth, you also have solar like neon that is trapped within the Earth. And the best way probably to put the solar gas into the Earth is into the mantle, into the deep Earth, is probably to think about the proto-Earth grew to a size that allowed to trap gravitationally nebular gas. This nebular gas triggered some greenhouse melting of the Earth, and also the accretion, the heat of accretion melted large quantities of the silicate as magma ocean, and this nebular gas equilibrated for neon with the mantle. And the mantle solidified, and now the nebular gas is still, nebular neon is still present. The other gas are just completed. It's just a mass balance problem because the nebula was quite rich in it. So we get another component to make the terrestrial volatile, and it's in fact there is a little bit of nebular gas. Most of the volatile on Earth are sourced by like a meteorite, by inner solar body, by planetesimals that form the near solar system, but you still have some nebular gas. And finally, I would like to show another example. It is xenon isotopes. That's another noble gas. It's a heavier noble gas, and it has 9 isotopes that are produced by different star-forming process, so-called air process by neutron merger, AGB stars by S process, and so on. So, in fact, the composition of all of elements in the solar system, including xenon, are due to a mixing between different stardust of different origin. And in fact, this was very useful to trace the contribution of comets to Earth. And in fact, we measured with a spacecraft, with a Rosetta spacecraft, with an instrument that was on board, a mass spectrometer. We measured the composition of xenon in the comet. And these are the results. In fact, these are the cometary xenon which is depleted in 136, 136 being air process isotopes. So, okay, air process isotopes here. Okay, so the cometary xenon apparently is depleted in air process xenon here. These are the primitive meteorite composition, and this is the primitive atmosphere of the Earth when the Earth formed. Since then, it evolved a little bit, but this is second. And so, in fact, you can make the primitive atmosphere on Earth by mixing xenon from comets and xenon from meteorites. And the mixing proportion is about 20% xenon from comet and 80% xenon from meteorite. This means that here we have also an evidence that the comet contributed some volatile element to the Earth. So let me summarize a little bit all this. Okay, the take-home message is that the volatile element in the solar system solids, ice, organic dust, and primitive meteorite have a composition markedly different from those of the nebular gas, both in elemental abundance and in isotopic composition. So you cannot derive the volatile we see on Earth directly from the solar nebula, except for a little bit of solar neon in the mantle. But all the rest, you cannot do it. So you need to have some processing that result in this. And the terrestrial volatile result from solution of nebular gas in magma ocean, that's for the case of neon. That means at some stage, presumably the proto-Earth looks like a small Jupiter with big enough, massive enough to already attract some nebular gas that dissolve in the magma ocean. But most of the volatiles are derived from planetesimal that are also now resent those of meteoritic material. And there was a limited, but quite very limited contribution of cometary volatile to the Earth, especially the Earth surface. I don't know how long do I have now? Maybe I will. There is a second part which is about the how to obtain this composition, and I will go quite quickly in this second part. Again, I will use noble gas, which are very useful physical tracers. This is again the noble gas composition normalized to the nebular composition, which is flat here. These are the primitive meteorites, this is the Earth, and this is Mars. So again, we see that we cannot derive directly in terms of abundance the noble gas trapped in inner solar bodies from the nebula. And we can go furthermore that also the isotope composition of noble gas, here exemplified by xenon, is different from the nebula. So again, this is normalized to nebula composition, isotope composition of xenon in the solar nebula. And in red is the composition of meteorites. So it's different. And in fact, you need to do something to fractionate this gas. And we have been attempting in the lab to reproduce such fractionation just by assuming that this fractionation arose from ionization of the gas, because there was ionization everywhere in the nascent solar system, either by radioactive or by irradiation by solar and stellar photon. So we just mimicked this ionization. It's a very simple experiment. We are flowing a gas of solar-like composition, hydrogen, nitrogen, and CO. And then here we ionize the gas with, in that case, electron impact, where we make a small plasma. And what we obtain, this is a zoom of this part, we obtain some black deposits, which is organic matter, okay? And we scratch this black deposit, and then we analyze noble gas in this black deposit. And that's what we obtain. We obtain some organics. This is the soot obtained in our experiments. This is the morphology of the soot, a different scale. And this is organic matter in primitive meteorite. So clearly, they resemble very much what you see in the meteorite. And in fact, we reproduce the elemental fractionation. Again, this is a Q, these are meteorites here. It's called Q for some reason. red is meteorite, and gray area are our result of our experiment. So we reproduce the elemental fractionation and the isotopes, this is the Zenon isotopes. Again, red is meteorite, gray area are our experiment. We reproduce more or less the composition of xenon observed in meteorite as well as krypton. Okay, so by ionizing the gas, we are able to reproduce what we observed in terms of elemental fractionation and in terms of isotope fractionation. And I will go quickly there because time is just to mention, sorry, as a group of scientists at the University of California, San Diego, led by Marty also explained or resulted or succeeded in enriched nitrogen by several thousand of per mil or several 100% in some experiment where they flew some H2N2 gas and illuminated this gas by synchrotron UV radiation in the same range and the solar stellar radiation, and they obtained huge enrichment in nitrogen-15. So the bottom line is that you can also explain huge nitrogen-15 enrichment by irradiation by stellar photon. And I am now almost done. So my final proposal is that in order to fractionate the abundance and the isotope composition of volatile element from the nebular gas, one way would be to ionize it and irradiate it with photon in the UV range, such as those of stars. So this is one example. Here you have H2 and CO. You decompose H2, you decompose CO, and finally you are able to recombine, do some photochemistry, producing some icy water, some frozen water, dust, that is hosting isotope anomalies. You also produce, in that case, you also produce, do some photochemistry with H2 to produce organic matter as done in the lab, and you enrich also in nitrogen. So just by considering a process that took place early during the formation of the solar system, maybe even before the disk epoch, the interaction between stellar light, either from nearby star or from the central star, allowed, or at least we propose it, allowed to fractionate the abundance of the element, that is to change the abundance of the element, but also to change the isotope composition, to produce the isotope excess we see, and also to stabilize in the form of solids those volatile elements, in the form of icy rain, in the form of organic dust. And later on, these solids were incorporated in chondritic and planetary material because they were already as solids, and then they could be trapped efficiently. Otherwise, we would not trap this volatile. Okay, so I am done now. Just to so the take-home message too. So ionization of gas mixture describes the structure of primitive organic matter and the noble gas fractionation. This is the lab experiment. Large enrichment in nitrogen-15 by irradiation. These are the experiments of the San Diego group. And finally, ionization irradiation by stellar photon was aimed to synthesize solid, ice, and organic dust that ultimately permitted their incorporation in the building block of the planets. And this is a summary of those processes. So we start with a molecular cloud fall onto the disk, the formation of the first solid by presumably by irradiation, by ionization, forming icy dust and organic dust, and condensation of metal silicate, which forms the first solid by accretion. Finally, this accretion of this solid form the planets. The early accretion of these planets provocates two processes, two concomitant processes: accretion of a nebular-like atmosphere and melting of the outer part of the planets. And finally, there has been some more events that I didn't mention, giant impact that formed the Earth's moon system. And finally, maybe late accretion of chondritic and cometary material. We believe that the cometary accretion probably took place at this stage, because it seems that it affected only the surface of the Earth. And voila, these are the people in the team that have been working since the last 5 to 10 years, thanks from a support from ERC. Also, we are very blessed to have young people working with us. And that is, thank you for your attention. And I'm sorry, it's my first talk, so maybe it was a little bit not clear, but thank you.
Bernard, thank you. We'll start with questions from the live audience first, followed by any questions from Zoom, if there are any. So, any questions? Yes, sure.
Did I understand correctly that the nitrogen isotope ratio can be explained if the Earth accrete gas early? I mean, during the solar nebula phase?
Yeah. In that case, the nitrogen isotope composition of the mantle of the Earth should be depleted in nitrogen 15, contrary to what you observe. We observe that the Earth is enriched in nitrogen 15, whereas if it was nebular, nitrogen should be depleted, or it should be poor in nitrogen 15. But in fact, as I said, it seems a little bit paradoxical that neon is from the nebula and not nitrogen. But this is because it's a mass balance problem. The protosolar nebula is very rich in the lightest element, including neon. If you mix up this material rich in neon with some material, chondritic material that is less rich in neon, you will see only in neon, but not on the other. So it's a mass balance problem. It's because the chondritic is depleted in neon. So even in the mantle chondritic, you see neon from the protosolar nebula because you have something that is rich in neon. But for the other elements, they are dominated by meteoritic.
So is there any evidence to support reaccretion or not?
Sorry, evidence for?
Are there any? So what we know about the early accretion? There was or there was?
We think that, in fact, the early accretion, it started with some dust, okay? And you already have some volatile elements that were in the form of solids, either ice or organics. Mm-hmm. And so the early accretion started by doing metal and silicate dust, incorporating this volatile element. And then you ended up, well, you don't end it, but this dust grew up more and more. And at some stage, there was some other process that permitted to grow to planetesimals. So from the beginning, you have this volatile rich dust that was incorporated during the accretion. And so you started by forming dust that is bigger and bigger. And Ramon and Steve has been modeling this. If you want to add something, you're welcome. But this dust grew up and to yield finally some planetism, some small planets, which themselves accreted to make bigger planets.
Can I follow up on your question? Because isn't it right, we were talking about this earlier, that Earth has solar neon in its mantle, but Mars seems to not. Is that because Mars escaped stage 3? Well, and Earth did not?
No, in fact, in the Martian mantle, there are no data for neon because neon is very depleted. we only have meteorites which are from Mars, which are highly shocked. So maybe neon is gone, or there was not. So we don't know if there
Okay,
is,
so you.
we don't know if there is solar
unresolved.
neon in the Martian matter.
But Jolt, there is a paper by Helmut Lammer, which was et al., which was published, I think, last year, in which we actually really talk about this, so that the noble gases in the Earth and Venus constrain the accretion time. And I think, if I remember correctly, it's been a while since we worked on this, but you need to accrete the Earth within about, to half an Earth mass, within about 5 million years. Otherwise, you're inconsistent with some of these isotopes. So that might be something to look into.
So my question address the problem that whether it was formed by a core accretion or double accretion or
Pebble accretion can only work if the pebbles came from the inner solar system, which is difficult to do because that reservoir should have been depleted within a million years.
If the Earth formed at the current position, yes.
Yeah, but where else would it form?
Anyway.
No, but then, as Steve showed like 2 weeks ago, then you cannot reproduce that volatility trend. And Earth and Mars are different isotopically. So then you need to have separate feeding zones, which means you cannot move Earth around without moving Mars.
There's not a lot of wiggle room. It's pretty tight all the way.
So it looks really likely that you need to form Earth with planetesimal accretion. In which case, the noble gases, at least in the Lammer paper, as we explained it, tell you that you need to do it really quickly. You need to get half an Earth mass in about 5 million years. Yeah, roughly. That's some of the best constraints that we have. But also the neon, from my understanding from what Bernard said just now, is that the neon in the mantle is telling you that when Earth was still an embryo, like Mars size, it accreted a little bit of nebular gas, which is now being incorporated, or has been, what is the word I'm looking for? Become soluble in the mantle.
Yes, magma ocean, so you can solubilize.
Yeah.
And the pressure has been estimated to not so high, maybe 100 bar of nebular gas is enough.
Yeah, but it's still a lot. Does that answer your question?
9%.
Yeah, you have to make the other 10% up.
Okay, so just collecting the proof of early Earth formation.
Yeah. Any other questions from this audience?
What is the main source of water in the Earth? Is it from accretion or impact?
Oh, that's a very good question. It's basically the isotope composition resembles to that we find in primitive meteorites that fall on the Earth, or that was sampled by the mission, dedicated mission. So the D over H ratio of the ocean is within the range of values you observe in meteorites. This means that it cannot be solar, nebular, and it can be cometary. Solar is depleted in deuterium, and comets are enriched in deuterium. So only the meteorite seems to have the meteorite has a quite large range of the OH ratio, but it encompasses the value of the terrestrial ocean. Within the Earth, in the mantle, we think that you have some type of meteorite, which are S-type chondrite, which could have supplied water. It's not water-rich meteorite, but if you have enough, you can do it. But again, it's a type of meteorite. So to answer your question, the terrestrial water is mainly coming from planetesimal that form in the inner solar system, or quite close to the inner solar system.
Attila?
Yeah, the neon isotope composition shows that we have a protosolar component in the mantle.
Yes.
Coming with the blue material.
Yes.
Is it possible that we have a protosolar hydrogen component as well? Because in the plumes, the hydrogen isotope compositions are a little bit lower than the M or B. So, what is your opinion about it?
Yes, there was a paper by a researcher called Alice that analyzed the DOH ratio with an ion probe in sand from a plume, which very high to ratio. And she proposed that she observed a negative value or depletion in deuterium in the samples, and she proposed yes that the mantle is still a real remnant of nebular hydrogen. I have some doubts which are more about the data, but this is technical, so I'm not sure about this. Yeah, that's possible. But one trick is that if you take the solar neon you have in the mantle and you take the hydrogen to neon ratio, for example, to see how much hydrogen you will put, you don't put enough. In normal condition, normal means in oxidizing condition as the mantle is now. If you are in more reducing conditions, then you could pump out hydrogen more efficiently. Put more hydrogen.
I would have another question as well. So when you look at the nitrogen and hydrogen isotope compositions, and we see from the meteorites that we have a range, a larger range in the hydrogen composition and a small range in the nitrogen.
Yes.
Is it possible that we have a chemical reaction producing hydrogen and removing the light hydrogen isotope? Yeah, that's it.
Yeah.
The former one.
Yeah.
And that's it.
Yeah.
So from the meteorites, those green dots.
Yeah.
So is it possible that it's kind of iron oxidation and removal of the light hydrogen?
Well, in terms of hydrogen, the variation are quite large. Some meteorites, which are carbonaceous chondrite, the type R, are effectively rich in deuterium, more rich than the average meteorite, and also have excess of nitrogen 15. I don't think that, at least for nitrogen, it's unlikely that this is a fractionation linked to some chemical reaction. But for hydrogen, one could think about, you would need to degas a lot of hydrogen probably to fractionate the top. So I think people now prefer to think about some components that was not equilibrated with the whole meteorite. Because quite often, if you look with a big microscope, an ion probe, which is a microscope in some way, you look at the isotope ratio, this excess quite often appears like spots. That is concentrated in a few places, the rest being normal. So people, I think, more think about a kind of heterogeneous material that was incorporated.
Anybody else? Yes, last.
How much of these do you think is testable in exoplanets with the current astronomical instrumentation? Because comparative planetology would require things like that, looking at the closest nearby exoplanetary systems and to check whether the patterns are the same.
I think that it will be possible to use a Geo-rate ratio, at least in the exoplanetary atmosphere. For nitrogen, I don't know. And for the composition, yeah, it will be possible. I think some people are working on this. Yeah, it's depending on the observation and the means. You know better than me, because you know better than that. But I think the isotopes could be possible for
Hydrogen, maybe.
Yeah, for the Geo-rate ratio. Because they see they can determine the Geo-rate ratio in some molecular cloud. So this means that if you have enough material,
Anybody else?
Maybe interstellar objects then. The poor man's exoplanet is an interstellar asteroid or comet like Oumuamua, which was not a starship, but was a natural body. Maybe that's
Borisov, right? Didn't they get some data from Borisov, and it didn't look that much different?
it was just the same as the comet.
It's just its orbit was fine.
But this is certainly a very promising field. I don't know if the James Webb Telescope will allow it.
Okay, people, let's wrap it up. Let's thank Bernard again.